to the Yata Memorial Lecture in Robotics. This is part of the School of Computer Science Distinguished Lecture Series. Yata was a postdoctoral fellow in the Robotics Institute until 2000, with her untimely death occurring in 2002. She was a graduate of the University of Chicago under the guidance of Professor Yata. She came to the United States, Carnegie Mellon. She served as a postdoctoral fellow in robotics for 3 years under Chuck Thorpe. Yata's accomplishments in the field of ultrasonic sensing were highly regarded and won her the Best Student Paper Award at ICRA in 1999. It was frequently noted, and we always remember, the quality of her work was exceeded only by her kindness and thoughtfulness as a friend. It's a good lesson for all of us. Join us in paying tribute to an extraordinary colleague and friend for this most exciting lecture series. And I am really excited that we were able to invite Brenna Argall. She is currently an associate professor of mechanical engineering, computer science, and physical medicine and rehabilitation at Northwestern University. She's the founder and director of the Assistive Rehabilitation Robotics Laboratory, Argall Lab, at the Shirley Ryan AbilityLab, formerly the Rehabilitation Institute of Chicago, the #1 ranked rehabilitation hospital in the United States. The mission of Argall Lab is to advance human ability by leveraging robotics autonomy. Argall's a fellow of the American Institute for Medical and Biological Engineering in 2023, a recipient of the NSF Career Award in 2016, and was named one of the 40 under 40 by Crane's Chicago Business in 2016. Her PhD in robotics is right here from Carnegie Mellon's Robotics Institute. Yay. As well as a BS in mathematics, also here at CMU, where we overlapped as undergraduates. Yeah. Prior to joining Northwestern and Rick, she's a postdoctoral fellow at EPFL, and prior to graduate school, she held a computational biology position at the NIH. More recently, in 2019, she was a visiting research fellow at the Weiss Center for Biological and Neuroengineering in Geneva, Switzerland. Please join me in welcoming Brenna.
Thank you, everyone. Thanks, Matt, for the introduction. And it's always great to be back at CMU and at the Robotics Institute. So as Matt mentioned, my lab is located in the Shirley Ryan AbilityLab, which is a rehabilitation hospital in downtown Chicago. We were formerly known as the Rehabilitation Institute of Chicago until in 2017, I believe. We moved buildings. We built a new hospital, and this hospital is actually founded on a model of integrating clinical research, or research with clinical practice. So you can see here that I'm walking with one of our research participants. That's my lab space, and actually it's inside of what would be normally traditionally called a therapy gym. So clinical and research work is happening in the same space within this hospital. The area that my lab works within is functionally assistive machines. So these are machines that are used after rehabilitation has plateaued, for example, but basically they bridge gaps in function that remain as a result of injury or disease. And across the field of functionally assistive machines, there persists a challenge in capturing control signals from the human body to operate these machines. Probably most notably is the control of upper limb prostheses using EMG, where you have a confound where the higher the level of amputation, the fewer residual muscles that remain to control a higher dimensional assistive device. But even if we look at the much simpler control case of the powered wheelchair, which is a 2D control problem, you control speed and you control heading, we have this confound where the more limited someone's motor ability, so for example, as the level of injury progresses up the spinal cord, the interfaces that are available for people to use become more limited. So we start out with way down here. You maybe can use a 3-axis joystick. You actually don't need that 3rd axis for a wheelchair operation, but that requires the hand function to be able to grip and twist, which not everyone has. Sometimes they can push the joystick without being able to operate it like that. Then we have a 2D joystick, or a 2-axis joystick. We have a head array, which is switches embedded within a headrest, which is a 1 or 2D control interface. It depends on if you can position things just right to activate the back and side pad at the same time. And even if you position it right, it maybe sort of loosens and changes throughout the day. Most critically, the transition from joystick to head array is a transition from proportional to non-proportional control. So when you deflect a joystick farther, you get a larger control signal, and that maps to, for example, a larger velocity command or speed command for the wheelchair. With a head array, you are now just operating a switch-based interface. So you're basically flipping a switch on or off that says go, don't go. If you want to actually change the magnitude of the control signal, you have to navigate your way back through a menu. So most wheelchairs today have a little menu that sits on the armrest. You have to navigate your way, by tapping your head, navigate your way back to a menu to select a different power level. And there's typically like 4 power levels with a powered wheelchair. With a sip and puff, things get even more difficult. Even though it is a continuous valued control signal that's being measured from the interface, it's a pressure signal from based on respiration, it is interpreted in a discrete way. So thresholds are set to interpret it as a hard puff or a soft puff, or a hard sip or a soft sip. So it ends up still being discrete control, and the only way to get this to be 2D control is to latch control in another dimension. So you basically latch forward motion, and then you can maybe control your heading while forward motion is latched. But this takes a lot of skill to be able to use. Okay, so, and all of these challenges that I just talked about, so first I'll show a video of what this looks like. So this is video taken in my lab quite a number of years ago. This is actually our old lab before we built the new hospital that I talked about. And on the left, you see this participant using a joystick, and on the right, they're using a head array. So you can see that the motion on the right is much jerkier, it's much more fragmented. But even on the left, this is a difficult control problem. So even ADA-compliant doorways only leave about a 10-centimeter leeway for most wheelchairs today. So that's, if you're going to be centered, that's 5 centimeters on each side. It's a tight control problem. And this person is an expert wheelchair driver. He's not necessarily an expert with our chair. He's not as familiar with our chair. And you see he's using a T-bar because he doesn't have that hand function to grip. But he's been driving a wheelchair for 25 years, and it's still difficult for him in that way. So all these challenges that I just talked about only get further confounded once the complexity of the device that we're trying to control gets greater. So here you see someone operating a Canova Jayco robotic arm. This is nominally a 6-dimensional control problem to position the hand of a robotic arm in position and orientation. It obviously can be even higher dimensional than that. That does not include actually operating the gripper or operating the hand. He happens to be doing it with his foot, which is an exceptional level of skill. But if you think about now trying to use these very limited control interfaces that only operate 1 or 2 dimensions at a time to operate this 6-dimensional control problem, it becomes further exacerbated. And of course, the irony is that someone who actually needs the help of an arm like this, by definition, can't use the kind of joysticks that are available there, or most likely can't. And so they're restricted to these very limited interfaces, and yet the device that they want to be operating is more complex. So here's an example from my lab of what it can look like to teleoperate a robotic arm using an interface. So you see he's using a utility cuff and a pen inside the utility cuff to actually push the buttons to switch between control modes. So the control space of the robot is partitioned into control modes. You maybe operate X, Y, push a button, you can rotate an X, and it requires you sort of knowing the sequence of mode switches. You see that he actually went back and started to operate the robot after a mode switch, and then realized he wasn't in the mode that he wanted to be in and had to push it again. So this is and he's actually using a joystick, only in two axes, only in 2 dimensions, but you can see how difficult this problem is, even if you're using a joystick. So to sort of recap what I was just talking about, or the points that I just touched upon. So challenges to assistive machine operation. First, the human impairment in itself. And this is masking and filtering the control information that the human would like to be sending over to the assistive machine. Then we have limitations of the control interfaces, or particularly the accessible control interfaces. They're limited in their dimensionality, they're limited in their continuity or proportionality. And then third, we have this catch-22 of machine complexity, where often the more severe someone's motor impairment is, the more complex is the assistance that they require. And so you build a more complex machine to meet that need, and it becomes more difficult to control as a result. So of course, a potential solution to help address these challenges is to introduce robotics intelligence onto an autonomy, onto these assistive machines, turn them into assistive robots that can share some of this control burden with the human. To sort of situate the work of adding robotics autonomy to assistive robots within the larger field of rehabilitation robots, when I think about the field of rehabilitation robots, I tend to think about it in these two big categories. So there are rehabilitation robots that are actually meant to rehabilitate the human body. So here we see the Locomat. This is a roboticized treadmill that will guide the human limb in movements that the physical therapist would like to see the person executing in order to actually rehabilitate their own body. Then there are rehabilitation robots that are meant to bridge gaps in loss function. So this is not rehabilitating the body itself. It's using a machine or a robot in order to bridge a functional gap. And within that category, two really critical distinctions when we think about adding robotics autonomy to these machines is whether or not the machine is worn on the body or not worn on the body. And the reason why is because when you add on robotics autonomy and intelligence, you typically are adding on sensors, you're typically adding on power for those sensors, and therefore you're adding on weight. And there's a big question on how to actually do that when the machine is being worn on the body. It's not that it can't be done, but it's an additional engineering hurdle to overcome. So most of the work in rehabilitation robotics that adds autonomy to the robot happens within this pathway. So it's robots that are replacing loss function and that are not worn on the body. All right, so we're adding sensing, we're adding computation and AI to these systems in order to turn them into assistive robots. And the real devil in the details is in this step, the computing and AI. So we know that people don't want a 100% driverless car solution for their assistive devices. They might in certain circumstances, but on the whole, they still want to be in the control loop. So what's the right way to now integrate the information that's coming from the human and that's coming from the autonomy? And getting that right is really critical. So what we want to pursue is partial assistive autonomy. And there are two big tenets that my lab focuses on as we are developing assistive partial autonomy. The first is that the control sharing needs to be judicious. And the reason why is because if the autonomy steps in at the wrong time or with the wrong control signal, we're actually taking away from the human's autonomy. We're doing the opposite of what we set out to do, and we don't want to do that. The second is that this idea that the information that the human is trying to transmit to the machine is masked and filtered by both their motor impairment and the interface that is accessible to them to use. And so I'm going to talk about both of these in my talk today. In the first half, I'm going to focus on this question of judicious control sharing. So a study that my lab ran a number of years ago looked at allowing the end user themselves to customize how control sharing was happening between the machine and the autonomy. So we used this sort of classic piecewise linear control sharing arbitration function, where the level along alpha, along the y-axis, dictates how much control is with the autonomy versus the machine. And there are, of course, 3 parameters that you can use to actually customize this function or change its shape. And what we did was that we performed an exploratory study where people are able to give us feedback that would change the shape of this function. So they could say things like, I wish the robot had helped me earlier, and we would slide theta 1. Or I wish the robot, when it started helping me, helped me more aggressively or helped me faster. And we could change the slope of this function. So this is exploratory. And what we saw, so you've already seen the without assistance video. I played that earlier. But with the with assistance video, you can see now that, well, all 6 control conventions are being operated simultaneously. That's the role of the autonomy. But you can see also that we were able to infer the user's intent fairly quickly in terms of which goal they were trying to achieve or trying to reach. But some interesting insights that we had from this study. So one was that we took a look. We had spinal cord injured participants and participants without any injury. And that's who you see in the red is spinal cord injury, and the black dots are without injury. And we saw a big statistically significant difference in their task completion time with teleoperation. As we amped up the amount of assistance by changing that arbitration function, we saw this difference becoming less pronounced. However, it only fully disappeared when they were using a shared control paradigm that they had customized themselves. And this surprised me. And the reason why it surprised me is because if you had asked me which of these paradigms I would have thought would have eliminated the difference or most dramatically, I would have said maximum, because custom lies somewhere between min and max. And the maximum paradigm was what engaged the autonomy the most. And the autonomy way of executing this was what was the same across all participants. But that was not the case. So people had some sort of an insight into how they were interacting with the autonomy that we were not capturing. There was also a suggestion that user-directed optimization was considering something more than what we typically consider as roboticists and our standard cost functions. So if we use task completion time as a proxy for time minimization, and if we use the number of mode switches, the number of times you have to push a button to switch between control modes, if we use that as a proxy for effort, we saw a number of cases where time was not being minimized by people and effort was not being minimized. And so the conclusions of this study was basically that people are interacting with things in ways that we aren't quite, and optimizing for things in ways that we aren't quite fully understanding and capturing. There's also a question of which shared control paradigm to use. So I just talked about how the end user might customize it. These are all different shared control paradigms that come from the robotic wheelchair literature. And at the time that we did this study, we had seen a lot of instances of comparing one of these given shared control paradigms to full autonomy or to no autonomy, or just comparing full autonomy to no autonomy. But what we hadn't seen was a side-by-side comparison of different ways to share control. So we implemented all of these shared control paradigms on our robotic wheelchair, and we compared them. And what you might notice is that they don't look very different from each other. And that's what we saw in the data as well. When we actually compared them in terms of things that we typically measure as roboticists, things like number of collisions, task completion time, they were not statistically different from each other. What we did see, however, was a difference in preference. So we asked everyone to rate their most preferred paradigm and their least preferred paradigm, and we allowed them to have as many ties as they wanted. And what we saw was that every single paradigm was chosen at least once as most preferred and at least once as least preferred by someone. What we also saw, so we were using, and we did do some work, I'll just mention, on trying to actually predict these preferences. I'm not going to go into that data right now. What we also saw, though, was that, so we had people come for nominally two sessions. Some of the spinal cord injured participants, we had to split their session in half because of their sitting tolerance. So it was 2 to 4 sessions, but most people it was 2 sessions. And in each session, they operated one of these 2 interfaces, so either a joystick or a head array. And what we saw was that 50% of the time, people switched their control sharing preference when they switched their interface that they were using. And we don't really know if that's because of the interface itself or because of they were starting to become more familiar with the autonomy. I'll highlight that this 2 to 4 sessions, so I just mentioned that we didn't really know if it was because of the interface itself or because of how familiar they were becoming with the autonomy. This is something that I think we as a field need to work more on. So these kinds of studies typically happen in 1 session, maybe 2 sessions. And so what we are really evaluating, and my own lab's work included, is novel interaction with an interface or with an autonomy paradigm. And of course, over time, people are changing. And over time, they are becoming more or less familiar with the technology. And so I think that we are severely limiting ourselves in terms of what we are learning when we perform such short-term studies. So I'm going to add that to my list of challenges for assistive autonomy, that longitudinal and real-world evaluations, where by real-world I mean outside of the lab, are really, really needed. They're not easy. There's a reason why they're not happening, but they're very important for us to be starting to give more attention to. Okay, so hopefully these 2 studies that I just presented convinced you of the need for customization within this space. Now, the big question, of course, is how do we actually achieve customization? And I have a couple of thoughts on that. So if we're actually having our assistive autonomy actually adapt, first big question is, where does the feedback signal come for learning? So if you aren't using an unsupervised learning paradigm, you need some sort of a feedback signal. It's either a supervised label, it's a reward, it's an example, it's something. So what's actually the best mechanism for this type of interaction between the human and the machine and the autonomy in order to have learning be happening and to glean information from what's happening? Do we want people to be giving corrections? Do we want them to be giving demonstrations? Is the way we're going to be performing learning explicit? Are we going to have a button that they press that they say, I don't like that, and we use it as a reward feedback? Is it going to be implicit, that they just take over control of the joystick and we say, all right, they're taking over control, they didn't like something that I just did. I don't know if they thought that the autonomy shouldn't have stepped in or it stepped in the wrong way, but something happened that they didn't want. Another big question is this masked and filtered information. So I already talked about how this is masking the true human intent, but there's also this question of whether or not the autonomy can trust the human. So we think about the reverse a lot in robotics, whether or not humans trust robots, humans trust autonomy. I would argue that in this kind of a domain, where it's a shared control system, and the reason for the shared control system is because there are difficulties or deficits in the human's control, that we need to reason about whether or not we can actually trust that control signal that's coming from them. Was it what they intended? Was it what is safe? Or is it safe? My lab has done some work on this second topic of having the autonomy trust the human. I'm not going to get into it in this talk, however. OK, there's also temporal considerations. So I already mentioned that people can be adapting, or that their familiarization with the technology is going to be changing over time. That happens with all of us. In this particular domain, you actually have that people's physiology is changing. So they might be regaining ability as a result of rehabilitation. They might be losing ability as a result of a degenerative disease. And so the fact that their physiology is changing in addition to their familiarity presents this challenge for machine learning paradigms. So is this a temporary blip? Do they just have more pain or fatigue today? And we shouldn't actually be using this to update our learned policy? Or is it something that's enduring? And actually, we need to be changing the way that we are interacting with them. There's also a question of the rate of adaptation. So if you adapt too quickly, you're going to make the system unintuitive for the user. But if you adapt too slowly, you're not going to be meeting their needs. And finally, there's this challenge of human autonomy co-adaptation. So of course, if the autonomy is adapting to the human and the human is adapting to the autonomy, you now have this co-evolution cycle. And actually properly designing your autonomy, your adaptive autonomy within that evolving cycle is a real challenge. OK, so I'm going to first talk about work that so right now I'm going to start talking about an evolution of work in my lab that started out as first looking into this question of learning. And it turned into a really in-depth dive into this question of the information being masked or filtered. So, sorry, just a second. OK, so a number of years ago, the topic of my career award actually was robot learning from motor-impaired teachers and task partners. Oops. OK, sorry about that. So here we have some video footage actually from my postdoc at EPFL, where I'm providing demonstrations to a robot, a high-dimensional robot arm and hand. And the only way to actually provide those demonstrations is actually to interface or sensorize my own arm and hand. Same thing on the left. We've got a tactile-based interface to provide corrections to a robot. Now the question is, if we want to achieve this kind of learning, where you can have sort of corrective learning or adaptive learning, where you can have end users define behaviors or caregivers define behaviors, how does that look when the person now has motor impairments and they're using these limited interfaces? So obviously, the interface I'm using on the right, totally out of the picture. And even on the interface on the left, perhaps wouldn't be an appropriate one. So in order to start tackling this problem, what we did was a large-scale usage characterization study. So we had a number of people come into our lab and operate our robotic wheelchair. And actually, there was no robotics autonomy, so it might as well have been a regular wheelchair. We did 62 sessions in total, 20 with spinal cord injured participants, 42 with uninjured participants. In each session, people operated a different interface. So we did 3 different interfaces. We did the joystick, which is 2D and proportional, as I was talking about before. The head array, which is 1 or 2D, depending on whether or not you can hit both of those pads at the same time, and is non-proportional. And then we also did a sip and puff, which normally, in the commercial sense, is a non-proportional interface, but we actually interpreted that pressure signal in a proportional way. So each time a person came in, they operated a different interface. Some of the spinal cord injured participants, all the interfaces were not accessible to them, so they didn't necessarily all do 3 sessions. And we had them perform 7 different tasks. So you guys saw video footage of these from my lab of these structures. So these are structures that we have within the hospital that replicate structures that are difficult to navigate, spatially constrained, within the environment or typical environments for wheelchair operators. So we had them perform 7 tasks, and at the beginning, I'm sorry that that's not showing up quite well. The videos are a little bit overlapped. But in the beginning, we gathered 3 baselines. One is a clinical standard, the wheelchair skills test. So this is used to evaluate both manual and powered wheelchair operation. But then we also came up with 2 virtual tasks that we developed ourselves in order to evaluate people's ability to operate the interface. So one is a command following task that just gave very simple command prompts and asked people to replicate them. And the second was a trajectory following task where we now had a simple 2D footprint of a wheelchair and just direction prompts and a path that you were trying to stay on. But there's more that involved now a little bit of path planning on the result or on the side of the person. I will just a little bit plug the fact that we've continued to work on these 2 different tasks, and at ICOR last year published a paper that has turned these into apps, and we're actually about to launch, actually it should even be in a couple of weeks, an evaluation by therapists for the suitability of these apps in evaluating interface use clinically. Okay. So we were not expecting in this characterization study that this first 5 minutes of data that we were collecting at the beginning of each session would be so rich and would give us so much information. But actually, just these trajectory and command following tasks gave us a number of interesting insights. So this is from the command following. What we saw, so we had uninjured participants and spinal cord injured participants. And what we saw in both cases was that there was not a significant difference in task success, so the ability to replicate these command prompts between the 3 interfaces. So no difference between the 3 interfaces, or no statistically significant difference between the 3 interfaces in being able to replicate the command. However, there was a significant difference in response time, depending on which interface was in use. Now, for the spinal cord injured participants, we could dig into this a little bit further because they are all wheelchair operators, which meant that for one of these 3 interfaces, they were an expert. It's what they used every day to operate their chair. So then we divided their data into expert and novice for the interfaces. And what we saw was that actually this difference in response time could improve over time. So this would be changing over time. Now, you might be wondering why this really matters. One of the reasons why this matters is because in shared control systems, we are using the control signal not only for control. We're often using it as input to an inference engine, for example. And it is being combined with information about the world when we are trying to infer where it is that we think a person is trying to go or what object it is that we think they're trying to pick up. And so if you have this delay in response time, it basically means that there's now a mismatch between the world state when the human generated the control signal or wanted to generate the control signal, and actually when the system, the robotics autonomy system, is receiving the signal. So we could look into this actually a little bit with the trajectory following task. So we could just do a very simple intent inference, which we actually do on our own wheelchair, where we forward project the control signal like a half a second into the future. And then we see if that's sort of we think that's your intended position, how close are you to it? And we saw that now the differences in intent, or the errors in intent inference differed based on the interface that was in use. Okay, and so then the last thing we kind of dug into a little bit more was that we thought, okay, what about if we remap the constraints of the interface? So the most constrained interface was the sip and puff. What if we remap these other 2 interfaces to match those constraints? And what we saw then was that some of these statistically significant differences in response time disappeared. And then the same thing with the people's ability to perform the task, the percent of time they were off the optimal path. So all of this told us that we were perhaps onto something. And we've now been pursuing this pathway that we're calling interface awareness in my lab in assistive autonomy. And what this interface awareness is doing is it is acknowledging the fact that in order for a human to issue a control signal to the machine, they need to physically do something. Even if it's a brain-computer interface, you're actually generating the electrical signal that's being picked up. So you have to physically do something in order for this control signal to be generated at all. And we don't normally model that within robotics. I'll just quickly mention that we actually sort of started thinking along these lines way back in 2016, where we actually constrained an A-star planner based on the interface constraints. So we constrained its cost function, or we represented these constraints both within the state action or the state transition function and also within the cost function. And what we saw was that when we did that, the planner started to behave a little bit more like the human operators. Okay, so typically within robotics autonomy systems, we represent things like this. So we have a task level action that we'd like to achieve. We'd like the robotic chair or the robot to go forward. And then there's some sort of a control command that will achieve that action. So you give a forward velocity and you get the forward level command. We're making the argument that this is a user interface agnostic representation, and there's actually more under the hood when the control signal is now coming from a human. So in particular, this control command, robot control command, is actually coming from some measured interface command. There's some interface that the human's using, and there's a measurement on that interface. Furthermore, there can be a mismatch between what they intended the interface to issue and what actually got measured by the interface. And so, I'm sorry. So what we've started doing is actually modeling this. So here, in this study, we gave people command prompts where we asked them to say, give a soft puff, give a hard puff. This was using a sip and puff. And then we build up a distribution of the stochastic deviations in the intended interface level command and the measured interface level command. What it can look like when this gets wrong. So let's say, for example, I'm in state X. So I'm operating, this is a state diagram for a three-dimensional robot control. So you can translate in 2 dimensions and rotate in 1 dimension. So let's say I'm in state X, and what I want to do is transition to controlling in Y. And to do that, I need to issue a hard puff. However, my threshold is shifted a little bit. It gets interpreted as a soft puff. And so what happens again instead is that I forward translate in X instead of switching to operation in Y. The second thing we do is we ask people to predict what robot control command or what interface command would actually generate these changes in robot state. So this starts to now dig into people's understanding of the mapping from the interface to actually robot control that they would like to see executed. So we build up distributions of both of these. Then we only provide customized assistance only if there's a mismatch between what we infer between what we think was their intended command and what actually got measured by the interface. So when we first evaluated this, it was in a very simple domain. It was using this 3D robot control, and the task was extremely constrained. What we saw was that we had the greatest efficacy with this kind of assistance when the person's ability to generate the control signal that they wanted to generate, an interface level signal. When their ability to generate the interface level signal was noisy, but they had a good understanding of how that mapped over to the robot control. So this was a very constrained experiment, however. And so what we're working on now is relaxing a lot of these constraints. So in particular, we're going from this 3D, a three-dimensional control of a simulated robot, and we're going to control all 7 dimensions where it's 6-dimensional end effector position and orientation plus operating the hand. So mapping that over to 7-degree of freedom robotic arm control. We're still using the sip and puff. And so what this looks like is we're going from this 3D state mapping of how the sip and puff, or state diagram of the states of the sip and puff, and it now maps over to something like this. This is actually the image we showed to participants, that this is what happens if you take hard puffs, you're going to do mode switching. Hard sips, you're going to do mode switching in the opposite direction. And if you're going to do soft sips or soft puffs, that actually moves you within your current control dimension, provides motion within the current control dimension. And to make this even harder, we're trying to do this in a task agnostic way. So we want to make minimal assumptions on the human's control policy. So I'm not going to sugarcoat it. This is hard, and we are not quite there yet, but we have done a case study with 2 spinal cord injured subjects. And one interesting thing that came out of this was that they were not actually able to detect the assistance when it was on versus off. So they couldn't tell. They thought that there was never any assistance. But when the assistance was engaged, they did report lower workloads using the NASA TLX survey of cognitive load, and they had fewer collisions. So I said that we were making minimal assumptions on the human's policy. The only thing we're assuming that we think they don't want to do is run into things. We assume that they want to be safe, but that's the only assumption we're making. Another thing that we saw was that training is critical. So this is confusing, right? This requires training. And so as we are building up this system and we're going to be doing a larger study that isn't just a case study, training is going to be a bigger component of it. And actually, we saw that even when we were doing this very preliminary work with the simulated system, is that their understanding of how the interface level commands mapped over to the robot control played a role. So I'm going to add this to our list of challenges for assistive autonomy, that you also have the human's understanding of the machine, of that translation from interface level command to machine motion. So the machine's control mappings and kinematics. And then once you introduce robotics autonomy, it further complicates this. Because of course now the command that they send isn't necessarily what gets executed. The autonomy might have changed it in some way. All right. So for the final portion of my talk, I'm going to return to this idea of the difficulty in capturing control signals. So work in my lab, for the first number of years that my lab existed, we limited ourselves to these commercially available control interfaces. And the reason why we did that was because they're commercially available, they're widely adopted, they're covered by insurance, and they've been extensively user vetted. So it's one less thing for people to adopt as you think of them of introducing autonomy into these machines. It is not to say, of course, that we couldn't necessarily do a better job or a different job if we had different interfaces. So this is a project that is in collaboration with Sandro Musovaldi, who's also at my hospital and Northwestern. And his lab had been working for some time on this idea of what they call a body-machine interface. And this is sensors on the upper body that they remap to a lower dimensional control point. And what they found was that you could have sensors on the shoulders of even someone with a cervical level spinal cord injury, so someone who is a quadriplegic, but you still, if it's an incomplete injury, they can still have a little bit of movement in the shoulders. And they were able to use that to operate a 2D control point, where that 2D control point could have been to type on a virtual keyboard. They even used it to drive a powered wheelchair. What we wanted to do in this project is map it to a higher dimensional control point. So we want to use it to operate this 7 or 6, nominally 6-dimensional robotic arm. And our plan for how we wanted to do this was to have robotics autonomy help with the human learning. So the idea is that we could have the human start with just 2D control. What those 2 dimensions map to was open for exploration. So here in this illustration, I show it mapping to 2 dimensions of control, but it could map to something else as well. And then we have the autonomy taking over the rest of the control. And the idea is that over time, we scale back the autonomy. The human takes over more and more of the control, so that in the end, ideally, the autonomy is not even there. And so what we're really trying to do in this project is to use robot machine learning to now elicit human motor learning. We've done a preliminary study on this project where we had 10 uninjured participants participate in 5 sessions each where they had full control of the robot. So we wanted to see what it looked like to have open-ended learning where it was not this phased approach and there was no autonomy assisting in the learning. So we just wanted to see what people did on their own. We had them performing reaching tasks, which you see on the left, and also some ADL tasks for evaluation, which you see on the right. And one interesting thing that came out of this study was that we divided these 10 participants into 2 groups. One was that there's 6 dimensions of control over controlling task space, and for the other 5, it was actually controlling joint space, the joint space of the robotic arm. And what we saw was a distinct difference on day 1 in the success in performing this ADL task. That people were actually, it was joint space that was more intuitive, which surprised me because this robotic arm is non-anthropomorphic, and it's not always intuitive, I find, the way that it moves in response to control signals. But that was the case. We saw that joint space was more intuitive off the bat. However, by day 5, they were the same. So it appears that there was a difference between the two in terms of their learnability. And we saw the same thing with trial time as well. So the second phase of this study is actually the meat of this work. We're going to have 20 spinal cord injured participants. We proposed 20 sessions each. We've redesigned the study. It'll probably be more like 15 or 16 sessions each. So it's still a big deal, and we're hoping to launch this in fall of this year. So I would stay tuned for the results of that study. Okay, so the final piece of work that I want to talk with people about is a new direction for my lab. My lab has never had anything translate out of its lab, but we are participating in the NSF Convergence Accelerator program. So for those of you who are not familiar, this is a program that is intentionally meant to perform convergent research that then results in research translating out of the lab, out into the real world. The topics that we are addressing in this project are barriers to independent mobility, 2 barriers to independent mobility. One is this question of capturing control signals from the human body, and the other is a lack of, in the commercial world, of very many, or almost any, assistance paradigms that can actually provide safety assistance. And what we're targeting with this project is that people will be able to operate wheelchairs with independence, even if they have very severe motor impairments. So we have a number of really excellent partners on this project. Team Gleason is a foundation that works with people living with ALS. And in particular, they have a group of people called the A-Team, who actually are people living with ALS who formerly had jobs within the technology sector. So they have both tech expertise and insight from living with ALS. Function engineering and relay robotics are both have expertise with bringing robots into human spaces out in the real world and with translating technology into commercial products. And then Lucy is our big collaborator on this project. So in 2020, the very first and still only commercial product to provide that is a sensor-based safety system, add-on for powered wheelchairs, entered the market. That's Lucy. We started collaborating with Lucy shortly after they came onto the market, actually. They got us a system donated to our lab and also convinced Sunrise Medical to donate us a wheelchair to put it on. And so we are rebuilding my lab's robotic wheelchair technology on top of this commercial product. And what we are aiming to do in this Convergence Accelerator project is first, add more aggressive intelligent assistance to the Lucy system. So Lucy provides subtractive-only assistance, so it'll stop you, or it'll steer you by selectively removing energy from your control signal. It does not actively steer you around obstacles, for example. So we are providing that active sort of assistance in one thrust of this work. We're also coming up with a novel control interface. So John Rogers is our collaborator who's a pioneer in the area of flexible electronics. And he has these very little sensors that have IMUs in addition to other sensors on them. They're flexible, they're wireless, and they've been used to monitor babies who are in the NICU. So they're very, very small. And we're going to use that to capture control signals nominally from any area of the body that still has residual movement. At least that's the goal. It's a big goal. It's not going to be accomplished by the end of this project, but that's our aim. And I should mention the reason why it's not going to be accomplished by the end of this project is that this is a 1-year project, and this is phase 1. Phase 2 we're going to be competing for this fall. So cross your fingers that we win phase 2 funding so that we're able to actually get some of this all the way out of the lab. The final thrust that we're working on is a little bit more of a nuts and bolts thrust, and it's about the communication between the input device and the wheelchair. So currently, this communication is unidirectional, and it's serial. So it's actually using an old DVI printer cable. And that is how wheelchair interfaces talk to a wheelchair. And the wheelchair sends nothing back the other way. So we're coming up with an API based on HID protocols that is going to provide bi-directional digital communication, and we're going to release this open source. And we're hoping to remove the needle of the industry a little bit by doing this. So that's it. Thanks for your attention. I'd like to thank my current lab members on the left and some alumni whose work was featured in this talk on the right, the institutions that I'm affiliated with, and also my funding agencies. And I'm happy to take any questions.
Questions?
Yeah.
Thanks for the talk. Very cool stuff. I'm wondering, like, how you're thinking about kind of like autonomous systems that have more like task level or semantic kind of autonomy, like slightly higher level task sort of abilities, and how that folds into this kind of shared autonomy structure.
Yeah, that's a good question. So I do think that it certainly has a role. I think that actually systems, there are a lot of end users who would like both, and whose preference about whether or not which one they want running actually can even change day to day. So people with cerebral palsy, with muscular dystrophy, they wake up with very, very different levels of pain, levels of fatigue, levels of tone and spasticity, and they want different kinds of assistance on different days. So I think that actually, far out, once we have very complete systems, having this high-level semantics, of course, I think it'll be a stepwise progression where you maybe only start out in known environments that you've mapped, and then maybe can go beyond that. But first we provide just this sort of immediate reactive assistance, and then you go up. I think that that's probably the progression that's going to make sense. So far my lab has been working at the lower end. Yeah. Yeah.
Thank you for the awesome and inspiring talk. This is sort of, I guess, building on that question.
Yeah.
The type of assistance you might want depends not only on your physical capability today, but also the task that you're doing.
Yeah.
So what role does context play, or do you see context playing in future assistance?
Yeah, I think that context, well, certainly as we start thinking about higher level, context plays a huge role. For lower level, I think context doesn't always have to play as much of a role. You can imagine, but even with the low level, it can start to, right? So for example, you actually want to collide with a table when you're trying to dock with it to eat, right? And so there is some context. There's some behaviors that perhaps require less context. That might be just the one context, and then outside of that, you say, in all other circumstances, I don't want to hit anything. So the context can be a little bit more granular. But I think as you start getting to higher level, then if it's actually that you're picking one thing, and maybe the person can pick it themselves, right? Maybe we don't need to automatically infer it quite yet, and so you don't need the context quite as much. But yeah, that's kind of my answer. That's sort of an everywhere answer. Yeah. Mm-hmm. Yeah.
So everybody's freaking out about natural language, obviously, ChatGPT
Yeah.
and all
Sure.
that. So is there any role now, or do you see any role in the future for, I guess, language as a control input tool?
Yes. It depends on what you're doing. I'll actually note that I think 30 years ago, there actually was a natural language controller for wheelchairs that was pulled from the market because you would train it on your voice, and the training wasn't as sophisticated. And so when people would get into emergency situations, they would change the tone of their voice. So they would train it on stop and then shout stop, and it wouldn't detect it, right? So, yeah, right. So obviously we've come a long way since then. I'm sure we're going to start to see these on the market, especially if you're pairing it with something like a Lucy that provides some safety. It's a very natural sort of thing. If you're already using a discrete interface anyways, you're no longer getting that nuance of control, so just being able to say the word makes a lot of sense. If we start thinking about these sort of higher level semantic sort of tasks, then selecting that task, being able to just speak it makes a lot of sense. There are, of course, users that we're targeting this technology for who can't talk, so it won't be a solution for everyone, but you can imagine that it simplifies things for a number of people. Yeah. Yeah?
Just out of curiosity, What happens if the autonomy does not trust the human?
So, well, I should condition that on the fact that there is always an override button. So the human can always override the autonomy. What will happen if the autonomy doesn't trust the human is that it's going to try to avoid a collision. And so it's going to stop the system. It could be that the person says, I only ever want it to stop me. It could be that the person says, I'm actually okay with it trying to drive me around it. I've seen it happen. I've seen it in use enough. I trust that capability. So if the system is super sure that this is not as safe for me to do, then I'm okay with that. So partly this will involve building up models of the human. Lucy already has a customized reaction time. With the idea that people can provide, they prompt them to provide a joystick command, and then they see how long their reaction time is, and based on having longer or shorter reaction times is how far of a buffer they provide. So things like that, where if you have a model of the human and their ability to use the interface, you can also reason about that. Yeah.
Thank you for the talk. I guess I'm just wondering what the biggest challenge is, I guess, you see in terms of commercialization.
In terms of commercialization, there's a number of challenges. So of course, to get things to market, you actually need to extensively test with users. That's a lot of work. Lucy's made the decision to be subtractive only, in part because it made their product FDA exempt, and that let it go to market much quicker. But if we want to provide more aggressive assistance, it might be that we are no longer FDA exempt. So getting that kind of approval, I think I've heard someone at my hospital, Levi Hargrove, gave a statistic recently where people try to develop low-cost hardware, low-cost software, all these sorts of things, and actually just the infrastructure to put it out there. So even if you gave it to people for free, but you maintained it the way that you need to maintain it, already makes it cost thousands of dollars. And so that's a real challenge. I think Lucy's had great success in getting their insurance to cover their product, even though it's not yet a line item on insurance forms, which is a big deal in the medical world. You want a medical code associated with whatever it is that you're trying to give people. Does not have a code, but they've been able to justify it. So I think, making it so that it's covered by insurance, making it so that it's been tested by end users, and that end users were involved in this cyclic design process, so we're actually meeting their needs. That's a big challenge. I will also say that the wheelchair industry is fairly resistive to change. There's a lot of inertia. The robotic arm industry is new anyways, so there might be less resistance there, but there maybe isn't any resistance there. But the wheelchair industry is a bigger beast. Yeah. Mm-hmm.
Thank you for the really insightful talk. One of the findings that I thought was really interesting was that sometimes people would prefer customization even when elect to higher task completion time or task performance measures that we thought would be better to bring down. And I think in an ideal world, we would maybe be able to build these customizable devices that also lower the task metrics as well. So I'm wondering, from your work, do you have any insights for how we should do customization well?
Beyond having the person in the control loop, no. So I would say I will fully admit that we don't fully understand that result. We did not go back and dig into it further, so there could be any number of things that were contributing to that. I do think that this idea of familiarization with the technology and the autonomy is huge. And until we actually get to the point where people feel like they can anticipate what the autonomy is doing, they really understand what it's doing, it's only at that point where we're really going to be able to get insight from them about how they would actually like to interact with it. It could be that if the autonomy played less of a role, they understood the system better, and that's why they preferred it, right? So.
All right. Well, can you join me in thanking Brenna one more time?